Assalamualaikum warahmatullahi wabarakatuh, and a very good day. Today we will finish our final chapter, which is the trends in biosensor and biomems, and this will be our last lecture through the YouTube, and I hope that you can study this chapter um, as smart as you can, because most of the topics that are covered here are something that is very important, as you can see from the past question. Okay, before we go into detail for the glucose biosensor, we just have a overlook of the biosensor market. Okay, usually for a high tech technology, okay, for especially if in diagnostic, in medical devices, okay, some large company, okay, needs to see a market in excess of $100 million before investing in a high risk development program. So we can see that, okay, biosensor is one of the high risk, okay, high risk device that been developed, okay, that been developed, and also carry some point of interest, okay. And we actually, there's a lot of things that we can use biosensors, but how much is the market can accept this, okay. So besides glucose and pregnancy testing, other large scale consumer market for inexpensive biosensors have so far is hard to be made. It's hard to be made, and then it is elusive. Okay, so it is not a success. Okay, apart from glucose and pregnancy testing, there are some now other type of kits. Okay, but it is not as much as the one contributed by the glucose and pregnancy testing. Okay, so the smaller companies, okay, have either been content to pursue opportunity with smaller market sizes or to develop niche instrumentation for R&D. So instead of going for consumer products, they went and they go for R&D instead, or maybe some specialized, maybe certain companies, okay, they need they need a biosensor, okay, I'm sorry, they need a biosensor for like for agriculture, to detect some type of chemicals, okay. Maybe this type of biosensor, okay, has been developed, okay. And indeed, most of the innovation in biosensors has been, okay, by startups, which have been willing to take the risk of breaking new ground in the hope of trade sale in the medium term or modest long term income. So this type of startups is what we call new companies, okay, developed by the R&D from the universities, or maybe like those graduate like you guys, okay. So you will try to, okay, you have some knowledge on this technology, and you try to develop your own biosensor technology. So okay, so this type of companies, okay, or this type of individual that the main contributors to the innovation of the biosensors. So for the first one, we have a study case, which is the challenges for biosensor market. Okay, as we have studied before, okay, including the chapters with Dr. Aziza, okay, we know that biosensors has numerous advantages, okay, but we can see there's limited application of biosensors which is available in the market, okay. So one of the reason to this situation is because of the market acceptance, okay. The market seems to be reluctant to accept biosensors as one of the reliable type of system to measure certain type of disease. Okay, and we have to see that the custom market is different from the traditional market for the IC industry. Okay. So some of the disease, okay, some of the way to, okay, some of the application should be competitive, okay, should be competitive with the existing laboratory based assay techniques, okay. And the hindrance is that, okay, some of the biosensors is expensive, okay. Maybe it is not as fast as the existing method, okay, and hard to be manipulated. So you have to consider all these three factors, okay. If you want to have a good and reliable biosensor, it should be cheap, okay. How much it will cost per test, okay. Is it fast, or is it acceptably fast, or can you easy to manipulate the biosensor, whether you can manipulate it at the measurement level, okay, or at the data, okay, at the data level. So you can use that, you can transfer data and so on, okay, for you to diagnostic the disease, okay. So among all these biosensor that have been a success, okay, blood glucose sensor is the best, okay. So we can see that 85% of the world market for biosensors is contributed by the blood glucose sensor, okay. And the reason of this success is because of the diabetes management, okay. Diabetes management, there's a high demand from the diabetic patients, okay. And then the other reason is that the stability of the glucose oxidase, which is the enzyme used as the biomolecule for the recognition of the glucose. Okay. So okay, let us go to the specifically for the glucose biosensor, okay. So this is just a history. The slide number 4 is about the history of our glucose biosensor, okay. Okay, it is start by 3 people, okay. And they start a company, okay, called Genetics International, and later on it is renamed as Medisense, okay. And they are responsible of introducing the ferrocene mediated electrochemistry of glucose oxidase to the market in 1987. So it is somewhere around 33 years back, okay. Another type of version, okay, is ferricyanide mediated glucose oxidase, which was developed by Boehringer Ingelheim, okay, and later Roche, okay. They purchased this technology from a small company from US, okay, Tall Oaks, okay. So if you look at the names, okay, the name is a major player in blood glucose sensor. We know Roche, okay, and even Roche have his her own branch, okay, in Malaysia, and also Medisense is another name in medical device, okay. And then there's another company, okay, from Japan as Kyoto Daiichi Kagaku, okay, and later known as Acre, okay. They use a similar mediated format, but they use a capillary field to draw in the blood from a pinprick sample. The fifth slide is actually nothing, but you can see that the reason, okay, why glucose biosensor is very popular, okay, and it contributes to the 85% of the of the demand of biosensor. Okay, it is due to the extraordinary needs and demands from the diabetic community. Okay, first of all, in any business, it should be uh, based on the demand. Okay, the demand and the supply. Okay, so the demand is a lot and it is stable. Okay, from one from one type of customers. So the customers for the glucose biosensor comes from the diabetic community. Okay, so okay, what does the reason of these needs? Because they need a careful monitoring and control of blood sugar. Okay, so if it is not monitored, okay, the patient won't know, okay, the amount of the glucose in the blood. Okay, so if you don't monitor it and it is there's a high amount of sugar, okay, it can cause to the horrific side effects. Okay, for instance, blindness, amputation, kidney and organ failure. So the need to monitor blood glucose sugar, okay, regularly drive people, okay, with diabetes to seek the most convenient technology, and the chronic nature of the disease turn them into a highly discerning customers. So okay, they need to monitor. Maybe okay, it can be up even like once a day. Okay, once a day and at least once a month. Okay, at least once a month. So so the demand is high, and then okay, there's a lot of okay companies that may offer a technology that is good, okay, reliable, and then it is the result is reproducible. Okay, so the patient, okay, will know, okay, this is the amount of the blood sugar that is in their blood. Okay, like say, like for instance, if they have 6.5 means that is stable. Okay, if it is more than 65 millimole, okay, millimole, so it is not, so they need to do some, okay, some action to reduce the amount of the sugar in their blood. So here you need to know, okay, in slide 6 is about the technology drive behind glucose biosensor. Okay, you need to know, okay, the reason, okay, the ferrocene and the ferricyanide electrochemistry, which is easy, okay, which is friendly, okay, to be implemented by the industry. Okay, another thing is that the adaptation of screen printing for the production of the disposable biosensors printed on the PET, polyethylene terephthalate substrate. So it is easy. Okay, you just print out the disposable biosensors. Okay, so this is convenient. Okay, for the use of glucose detection. Okay, and then the instrument design pen shaped device. Okay, so okay, even though some of it doesn't look like pen, but some of it, okay, have that type of design. It is easy, okay, easy to be carried, okay, easy to be keep, okay, by the user. Okay, and then the capillary fill applying a small pinprick blood sample, so it doesn't need a lot of blood. Just one drop of blood will be enough. Okay, just one drop of blood will be enough. Okay, that you can put on the sensing strip. Okay. For slide number 7, I don't want to go in detail. Okay, you can have a read on the slide. Okay, this is about, okay, possible engineering improvements. Okay, every type of device, okay, actually you can furthermore, okay, you can furthermore improve the design, okay, and maybe you will make it more adaptable to certain applications, okay. So there are few things that you can do, okay, maybe in terms of what we call the in terms of the packaging, okay, in terms of, okay, how fast that you can unpack, okay, and maybe in terms of how do you keep it, and then maybe, okay, in terms specifically for blood glucose, okay, how you make it more comfortable for the patient, okay, does okay, can you make the blood sampling better, okay, is it painful or not, what type of needles, okay, okay, what type of needles you may use, and also instruction for the nurses or for the end user, okay, where is the most comfortable part, okay, for the patient to prick and get the sample, okay. Other type of the improvement, okay, stated there, okay, about the image, okay, about the possibility of taking blood from kids, so okay, maybe they can plug in or make it couple it together with game station, to encourage the, okay, to make the child, kan, not to be afraid with the blood glucose sampling. Okay, for slide number 8, is about the other subtopic in this chapter, okay, which is about the motivation and trends in biomems, okay. It is not just limited to this type of trends or motivation, but this is just a guide, okay. So the advances in biomedicine, microdevices and informatics, okay, are merging to provide new technologies that couple biological process into in silico models, or the technology based on the silicon, like microfabrication, okay. The new biomems applied in lab on chip artificial organs implantable biosensors may combine these techniques as stated in the slide, okay. These devices may on and will revolutionize specifically laboratory diagnostic, drug discovery, therapy and environmental monitoring. Slide number 9, okay, tells us about the relation, okay, the relation of the sizes, okay, which we can see in the table from 1 nanometer up to 1 meter, okay, and this also involves volume and times, okay. So these are the aspect, okay, that the biologists, microbiologists, biomedical engineers, physicists and all scientists and engineers around the world want to control, okay, and also study in the biological system. Maybe, okay, in the past, like during the Darwin time, during the Victorian age, okay, people study about the animal, okay, the organism itself, but later on, okay, we try to go down to the molecular level, okay, molecular level about of the organism, so that we know that maybe there are few aspects. For instance, like now we are having problems about COVID, okay. Are there any other solutions, okay, maybe in terms of like how to treat the COVID, how to treat the patient, maybe a better way of combating COVID-19. So it may go down even like down to 1 nanometer if we are going to fight this type of viruses. Slide number 10, okay, shows uh, the possibility of overlap, okay, of the technologies that we are working on, okay. it may not overlap, okay, with some other technologies, but sometimes there are some studies that may be overlap. For instance, like for instance Biomems, maybe it may overlap with tissue engineering. Okay, depends on the size of the studies. Okay, like we can see that from the 1 nanometer up to 10 millimeters. Okay, and then from the molecules and animals. Okay, so there are, if we want to go for you want to expand and we want to study further, maybe we need to see that, okay, there might be a possibility, like for instance to venture bio nanotechs. Okay, are there any other area that we may expand and extend, okay, our study into microarrays, okay, maybe in microfluidics. So if we can make a plot like this, okay, maybe we can relate, okay, what are the type of study that we want to do next time. Okay, slide number 11, okay, shows that current technology that is studied in Biomems and Bionems. Okay, so if we look at the electronic and also the semiconductor systems, okay, we manipulate just the hole and electrons. Okay, but how about if we can manipulate the information that is provided by the biological system, which is more complex. Okay, we have other issues, maybe about maybe related to the temperature. Okay, our biological cells cannot withstand high temperature and so on. Okay, but let's say if we can manipulate or study, okay, how does the biological system works, that if we look at our own body, for instance, there's a lot of things connected together. This is human. How about if we look at the lower level of life, okay, like for instance viruses, microbes. Okay, so they also offer some complexity, okay, if we compare to our own robot. So we have to appreciate, okay, how does the living, okay, creatures react compared to the artificial life that have been created by human, okay, such as a robotic system and so on. Okay, so okay, the full specification or state of a single living cell might require 100,000 parameters. This sentence shows how complex is a living cell. Okay, today biological and biophysical measurements often suffers from serious limitation. Okay, so if we want to measure, for instance, we have to measure cells, okay, in large numbers, like 1 million cells. Okay, so we have insufficient high frequency response or bandwidth for the dynamics of the phenomenon to be measured, and some measurement can only most of the measurement can be only taken at a single instant in time on a large, okay, non-differentiated population of cells. So if, okay, we can just monitor one cell, okay, maybe we can study, for instance, a fluorescent microscopy allows a spatial localization of 5 to 10 different proteins in a fixed sample, dynamic recordings of 1 or 2 protein in living cells. Okay, so but we have issues about the temporal resolution and sensitivity. So there's a lot of things that maybe we can improve, okay, in terms of like a measurement and so on, for the cells, and even like for at the molecular level, if we can. Okay, slide number 12 shows some points on what type of technology that we are looking for. Okay, right now, for instance, microarray technologies allow the measurement of the expression profiles of thousands of genes. Okay, these data are far from sufficient to specify quantitative dynamic cellular signaling and metabolic models. Okay, so maybe we need more data, okay, at profiles of more more of these genes. Okay, and then this is one thing that we should take care of, like the major gaps between the computational vision, okay, or modeling, or any type of modeling and simulation, okay, with the experimental. Sometimes we have to simplify many things, okay, and we have to discard, or maybe we have to ignore some parameters or some condition, okay, and this is like it doesn't tell her, okay, it tells us something, okay, but it doesn't solve the whole problem. So this major gap that we have to fill in. Okay, other type of issues, okay, like for instance, can we miniaturize, okay, the micro total analysis system, okay, can we make a micro bioreactors, okay, to culture cells itself, okay, culture yeast, bacteria, okay, or even like mammalian cells, okay, and also maybe if you want to measure, okay, like the extracellular action potential, okay, from like the cultured nerve or cardiac cells, okay, this requires microelectrodes, okay, maybe we need some like to measure, okay, cell metabolism and its response to toxins, okay, using maybe like electrochemical transducers or optical sensors. Maybe you can use this system. And then okay, the measurement of heat generated by 100,000 cells. Okay, and this is an issue already. But how about if like 10 to 20 cells or even one cell? So these are the things that, okay, that is nowadays is still complex. Okay, and then maybe how to measure the electrical impedance of a cell. Okay, so the next revolution will involve dynamic instrumentation of the single cell and integration of this biologically active element into the micro world, okay, associated with the silicon technology. Slide 13, okay, is a typical block diagram of a control system. Okay, we have a sensor, we have actuators, okay, we have a CPU, okay, we have a control mechanism, okay, to that works with the cell, okay. So this is the area that it is very interesting. Okay, you have a sensor, okay, a sensor. Maybe you want to measure an optimum environment for a cell. Okay, you have a sensor, maybe a heat sensor, and then if let's say, okay, the cell response gives a response of a lower temperature, okay, you can, okay, it will give a feedback to the to your control system, okay, to your CPU, to your control system, and then it will, okay, it will react with the actuator, okay, maybe to increase or maybe to lower the temperature, okay, for the environment. So this is one of the example, okay, if let's say you want to okay, you want to study, okay, to study about the behavior of a cell, okay, something that may happen, like for instance, maybe you want to study about a cancer cell, okay, how you want to kill it, okay, without affecting other normal cells. So this diagram will be good, okay, for to express what type of study you want to do. Okay, slide 14, it is an extension of the slide 13. Okay, it tells us the two things. Okay, it's about how you want to measure the metabolic rate and also the signaling trajectories of eukaryotic organism or mammalian cells. Okay, so I just want to summarize the whole slide. Okay, so if we can see that current technology, okay, in the bioreactors, it involves like changes, okay, it changes like hours, okay, or maybe days, okay, of the changes for in these bioreactors. Okay, but what they know, what we know, okay, from the study, okay, from the experimental work, the cell metabolism actually can change very fast in microseconds or seconds. Okay, so if we, let's say, we understand this phenomenon, one thing, and then we can create a type of control system, okay, which is very efficient. Then with a new type of technology, okay, so we can have a better type of control system to control the environment for the cells. Okay, slide number 15. Okay, this is what the scientists, okay, the researchers are working on. Okay, you can see that there's a new terms, nanophysiometers. Okay, so we may measure some the biological response in nano, okay, with the nanoperimeters, and also picocalorimeter. Okay, picocalorimeter. So it is it's smaller. Okay, it's much lesser than nano. Okay, so there are things that we can measure, okay, from a single cell or small population of cultured cell in sub-nanoliters. Okay, cell culture chamber. Okay, so there are things that maybe we need that it is interesting for us to measure about the heat generation, the oxygen consumption of the cell, extracellular pH, okay, glucose consumption, lactate production, okay, release of specific hormones and chemicals of the cells, and also other like quantities, for instance, oxidation reduction potential, transmembrane potential, calcium concentration, and expression of selected genes. So, okay, this is important, okay, because maybe we can create a new medicines to cure cancers, okay, and maybe we can improve type of drugs that we can that is used, okay, for treating blood pressure problems, diabetes, and everything. So, okay, all this study is not just for journal publication only, but this has a real application. Okay, slide 16. This is interesting slide. Okay, it shows us how can we as engineer, okay, as a biomedical engineers, okay, can contribute to bridge the gap in biological research. Okay, let's look at the second statement, second sentence. Okay, all these points, okay, the use of drugs, okay, gene knockout, RNA interference, okay, all these are more related to the work of the biochemists, okay, of the microbiologists, of the biologists, okay, at the cellular level. So if we look at this sentence, it's like, okay, it's not for us to solve this problem, but actually, okay, if we want to improve the technology, that's where we can come into. Okay, although they can what we call solve the problem in terms of biology, okay, but we can help it to be better because we introduce, okay, these engineering parameters or physical parameters. For instance, okay, like how about if we can, for instance, okay, introduce a small valve control channels, okay, to adjust the dynamically extracellular concentration of key substances. So this may help the biochemists, the microbiologists, those who work, okay, maybe we cannot say the genetic engineers, but those who work in this this cellular scientists, okay, this microbiologists, okay, how to solve this type of problems. Okay, maybe we can also apply electrical fields. Okay, maybe they are not used to because they are not trained in this field. Okay, but we can contribute in terms of the electric. Okay, we can use electrical fields. Okay, maybe mechanical stresses we can apply to individual. Okay, mechanotransducing and contractile cells. Okay, and even at the subcellular structures, maybe we can help them by uh, applying the optical probes. Okay, maybe from there we can trace or follow different biochemical changes, and then maybe we can also control the injection or withdrawal of fluid across the membrane of cells. Then using the Biomems devices, okay, maybe we can also apply optical control of drug or reagent release within a cell. Okay, and then maybe we can also use other type of biomems, for instance, and nanovalves. Okay, optic leakage compounds, nanotubes, and so on. So these are the things that we can contribute to the biologists. Okay, to solve many type of problems that we have now. So this will be the okay, starting from slide 17 will be the last subtopics, okay, in this chapter, which is about the drug delivery system. Okay. Okay. So this drug delivery system, we want to know, okay, what are the structures involved, okay, and then what are the advantages, okay, what are the future that lies, okay, in this type of systems. Okay, so the opportunities for improved drug delivery using biomems. Okay, we can introduce low dose vaccinations, okay, and painless transdermal drug. So in currently, okay, we use we use higher dose of vaccines. Okay, higher dose of vaccines because of the target area may be not as accurate as maybe in the future. Okay, but if we know that, okay, the target area, we know the target area, where is the target area in our body, okay, and we can send it efficiently. So why not we can use a lower dose vaccination. Okay, and maybe, and by using the drug delivery system, okay, we can introduce a painless transdermal drug. Okay, so this delivery may be possible if we can use the micro needles. Okay, so we can pierce the skin barrier layer, okay, into the capillary without reaching the nerve. So this will be painless. Okay, and then with this type of technology, okay, it should be low power. Okay, we can use a low volume, okay, with the help of Biomems pump. Okay, and then the reservoir is small, is very small, it's a micro reservoir. So that is it is implanted. Okay, and then the drug formulation, okay, maybe it is geometrically complex, extremely uniform, micro or nanoparticle, okay, which is formed through micromolding or with microfluidic devices. So this, okay, this drug delivery system can be intelligently navigate each drug molecule to the exact location where it is needed at the exact time when it is needed. So this is like a dream comes true. Okay, slide 18. Okay, it is about the how does this drug delivery system can be made. Okay, we can use common photolithography and other fabrication techniques that have been introduced, especially in chapter 1. Okay, so if we apply these techniques, okay, we can able to miniaturize, okay, miniaturize the drug delivery system. Okay, and this enables this quality or characteristic to be achieved. For instance, is rapid, okay, painless delivery of drugs into the skin. We can have micro pump or micro reservoir systems, okay, that can be implanted anywhere in the body. point of use drug formulation, okay, and extremely uniform micro and nanoparticles with complex geometries and functionalities for injection or injection. Okay, so we can incorporate this drug delivery system into electrodes, catheters and stents. Okay, and this can be integrated with sensors, computer controls and wireless telemetry. Okay, and it is projected that to grow 5% from the $132 billion in 2015. So if let's say it is more now, it can be $200 billion. Okay, nowadays. Okay. Slide number 19 is simple. Okay, it is about what type of photolithography technique that can be used. Okay, please study this. Okay, about the coating with photoresist and so on, and then you have the pattern that you require. Okay, to build the microchannels, and this make this technique can be used to create microneedles, actuators, valves and reservoir. Okay, now we go for one of the important topics for the drug delivery systems. Okay, it's about microneedles. What are the issues that motivate the application of microneedles? Okay, so we can see that if for the oral digestion of drugs, of medicine, there are possibility of being destroyed in the digestive tract. Maybe it is just passed through without being absorbed by the body, or maybe it is absorbed but immediately rejected by the body before reaching the target. So these are the three issues that they may affect the medicine if you consume it through oral. So if let's say you can avoid this, and then you just pass it through the to the bloodstream, maybe this can reduce those three effects that have been mentioned before. So first of all, you need to know the anatomy of the skin. So let's say the problem with this type of delivery is about pain. It's about the pain. So now you have to understand that for the anatomy of the skin, where does the nervous system? So if let's say you know that this capillary lies above the nerve systems, maybe you can transfer it to the capillary. So maybe you can target it. You can use as the administration target for vaccines. Like I told you before, issues regarding to delivery by needle, there might be pain, there might be fear associated with needles, and maybe about the safe use of needles. So to overcome this, you need to make sure that the needle is these microneedles are sharp enough to penetrate the stratum corneum. It is not that it's not that long. Like if we go to the previous statements, it should be like not more than 20 to 50 microns, the needle. So it should be efficient, so that it will let the drug to penetrate and deliver to the bloodstream. Slide 21 and slide 22 shows about the type of microneedles. We have solid microneedles, we have coated microneedles, we have biodegradable needles and hollow microneedles. Do read these two slides, because it tells you what type of needle, okay, the structure of needle. For instance, solid, okay, solid, you apply the therapeutic agents or the drugs on the solid microneedles, and then okay, it will penetrate and diffuse into the body. So this is how does it work, okay. And then we have the coated microneedles, okay. So it has a pre-coated drugs, okay. And then it is good, okay, for large molecules, okay, like for instance hormones, vaccines, and DNA, okay. But the limitation is the size of the dose that can be administered, okay. So you have to make sure that the whole dose must adhere to the needle during penetration. So for slide 22, it shows the biodegradable needles, okay. So it should be dissolved when it sticks into the skin, okay. Advantages because it is the drug itself, and then it eliminates the generation of the biohazardous waste. But okay, disadvantage maybe it is less robust mechanically compared to the solid microneedles, okay. And maybe the design, okay, will be complex, okay. And then you have to balance between the degradable material and also the efficiency of the sharpness of the needles, okay. And last one is the hollow microneedles. Okay, this is the one that in our mind, okay, if we talk about the microneedles, okay. Okay, it can deliver, okay, the liquid formulation rapidly by infusion. But however, because it is you have to consider it is micro, and also it should be hollow, okay. So it may break off in the skin. So there's few issues, okay. And then okay, you may have to seal the shaft of the needle, okay, to prevent leakage of the drug. Okay, final for slide 23, it just shows you types of hollow needles, okay. You have A, blunt cylinders, B is a bevel columns, C you have a metal conical, D you have off-centered volcano style, E citadel style, and the last one is the sawtooth style. Okay, slide 24, okay, we start to go for the actuators, okay. Here we suggest that the simplest way to dispense a drug is by osmosis. Osmosis is okay. You have learned it from your STPM, from matriculation, and maybe from your diploma. Okay, it's about spontaneous net movement of solvent molecules through a partially permeable membrane into a region of higher solute concentration in a direction that tends to equalize the solute concentration on the two sides. So this osmosis properties is important, okay. A semi-permeable membrane covers a solute, prompting an osmotic pressure differences that drive solvents, okay, usually water from the body, into the solute chamber. This solvent displaces drug, pumping the drug out of the device through a small orifice. The drug itself can be solute. Okay, so the entire device consists of single chamber with a semi-permeable membrane and small orifice. Okay, by using a different solute separate from the drug by a piston or flexible membrane, the osmotic pressure and hence the drug delivery rate can be independently controlled for any liquid drug formulation. By adding an adjacent reservoir to supply the solvent, the entire device can be operated independent of its surrounding. Okay, slide 25 is interesting. Okay, it shows a schematic of electrolytic pump, okay, for ocular drug delivery powered by wireless induction. Okay, when external induction circuit is on, which is in the bottom, electrical power transferred to the implanted pump drives and electrolytic reaction, generating bubbles which expand the bellows and displace drugs into the eye. So this is a good example of a pump, okay, to that is used for ocular, okay, at the eyes, okay, drug delivery system. Okay, in this topic, okay, we go for the valves. Okay, some implantable drug delivery system doesn't have actuator, okay, but it is controlled by active valving. Okay, so the drug reservoir is pre-pressurized, okay, and the pump actuation use valving such as thermal deflection of shape memory alloys or metallic bilayers, okay, and the channel of is constricted by magnetic or thermopneumatic methods, okay. Some other systems include piezoelectric valves, okay, including a dual valve manifold for multi-drug delivery with integrated pressure sensors, power supply, control circuitry, and spring-loaded reservoirs. Okay, the valves can respond directly to the environment without electronic control, and usually it is made by stimuli-sensitive hydrogels. Okay, slide 27 shows an example of a microfluidic valves actuated by stimuli-sensitive hydrogels. For this slide, okay, slide number 28, talks about the reservoir. Okay, this type of reservoir, this is not the only type, but this is one of the example of micro reservoir. Is already defined the microdose, so you don't have to meter, okay, meter or have a valve, okay, of the micro reservoir. So the system, okay, it uses gold films to see individual micro reservoirs, okay, until the target is reached, and then the cap, okay, the opening is melted away by electric current. Okay, so for slide 29 and 30, it is example of a micro reservoir that can be made from okay, from a cube, okay, on the slide 29, and then you have a like this mesoporous silicon microparticles, okay. So you have already you can it can contain and a significant amount of liquid inside the microparticles. So this also can act as a micro reservoir. Okay, so I would like to thank all of you, especially for Siti Fatimah, for helping me throughout the lecture. She's the one that helps me to create the YouTube video for the lectures, for the all the five topics that we have covered. Okay, may Allah, okay, may God bless her for her efforts, and I would like to thank all of you, okay, for listening to the lectures, okay, and I hope that all the contents will be useful for you, not only for the purpose of examination, okay, but I hope that if one day you venture into the R&D of MEMS and Biomems, okay, it will this course will act like introduction, okay. You know where to find, okay, where do you want to find the tools, where do you want to find your information, okay. And I hope that since this topic is it's a hot topic, okay, especially if you want to do masters or PhD in the future, so I hope, okay, you can use the knowledge that you have here as as a guide, as your first guide, okay, to your master's or PhD journey. And I hope that, okay, if you have the opportunity, okay, to work in advanced lab, okay, in this topic, I hope that whatever that myself and Dr. Aziza had contributed, okay, will be beneficial for you guys. Okay, and I hope that you guys will have a good future, okay, as a biomedical engineer, and also as a researcher, or and also as an engineer. Thank you very much, and I hope that every each of you will be successful in the future. Thank you so much.